can you guys see my screen? Okay. So let us continue this then. So we are continuing. Okay, I'll just turn on my video. Yeah. So we are just continuing mock test discussion, mock test 3. So we have gone a bit slow in the discussion, but I think in the process we have learned, yeah, more things. Mock test 3 discussion. And yeah, so the first two problems we have cleared. First problem had some issues, but yeah. Third problem, let's try to see. So this should hopefully be easy. And so let us see. So this is about a trapezium. So here is the thing. Yes, Adish. Yeah, now we can hear. Yeah, but it's very low. But maybe I can increase my. I think it is fine. Yeah, I can hear you now. Yeah, now it's, I think, perfect. Yeah, it's loud enough also. So we are looking at this trapezium ABCD, and AB is parallel to CD and F and E are midpoints. Yeah, so I think I gave this problem because I myself was having some conceptual issues with this earlier at some point. Maybe now also I have, I'll see. So we can clear it. F and E are midpoints of AD and BC. So F and E are midpoints of AD and BC. So sorry. And now we want to, so we also know something else. So we know that ABEF is twice the area of FECD. So sorry, ABEF is equal to, so the area of this is twice that of FECD. Okay. And we also know the midpoint. Now, using all this, we want to figure out the ratio of AB to DC. Okay. Find AB by DC. Okay. So yeah, so you guys can tell me how you do this if you have done it. Yes, yes. Now this is perfect, I think. Yeah. You can tell he's not saying now, so you can say first. Better. Okay. You drew both the diagonals. Okay, so let's see. So we are going to, one is enough. That's why I said both. Yeah, so one is enough. Okay. But why is FT parallel to CD? It's simple, but what is BPT? I don't know. Tell the full thing. Okay, but just say what because I don't see the proportions in full, because I don't know. If you look at ADC, then we don't know about AT, but okay. So how do you do that? FAT. Okay. No, but that's what we don't know, right? That is the point. So it is what you're saying is certainly true. Okay, but let's just think, how do you figure out? This is an interesting, easy thing, but so we have joined the midpoints of the side, and we want to say that this line is parallel to the two other lines, which are already parallel. Sorry, ABC and no, they are not symmetrical because BC is not equal to AD necessarily. Mm-hmm. Yeah, that's what. Yeah. So how do you show that? No. How? How? No, you cannot say that. To say that, you are already using that TE is parallel to BA. Yeah, Adish say. So it's no, it's not given. Okay. ACD. Um. Wait. Sorry, say that again. ACD. Okay. Mm-hmm. Mm-hmm. You cannot say it's a yeah. Hmm. So you see, it's a simple result, but we are getting okay. That's fine. So you can forget. Ah. Okay. So you are saying that you'll make this parallel like this, and then you make this parallel like this. And then you will show that, let's say this is T and this is T prime, and you want to show that they are the same points. How do you do that? Yeah. That is easy, right? That is easy because now you can use your similarity. Right. So now you can show this because now using similarity you can show because AT will be equal to TC. So T will be the midpoint. But then again T prime C will be equal to AT prime. So that T prime will also be the midpoint. Yeah. So from here we can from the construction we can so we can say that it is parallel. Okay. That's the point. So it's a simple result, but in an exam situation, it is possible to get, spend a lot of time struggling with this, and which we should not. But what will be a more safer way to do this? So what you can do is you can extend this to the triangle, and then you can apply your, I hope, your similarity results, and then you will surely get it. Right. If you extend this to a triangle, right? If you extend this thing to a triangle, then you can apply the similarity 2 times and so on, maybe, and you can, yeah, you can do it. So that's another way. So there was one more interesting way to show that this will be parallel. 1 minute. Just 1 second, okay. But anyways, I'm missing that, so leave it, yeah. So we can say that FE is parallel, okay, to these two. So yeah. So then what do we do? Hmm? Okay, so this is, you're saying X and this is Y, like that. FE is X plus Y over 2. Right. And then you can just do the calculations and you can do, yeah. So what is the answer? What does it turn out to be? Anyways, yeah, so that's fine, yeah. So from here it is easy to do, okay. So the key thing really was to show that this is parallel to this too, okay. FE is parallel. So a similar result, a similar problem is this, and this is also a very good problem to try. It's easy, but it has very good consequences. And so you guys can try this for homework. I am taking this, and then I am simply just taking the midpoint. Okay. Or should I, just a second? Yeah, I'm just simply taking the midpoint. Okay. And then you draw this line, or let me not. So let me do it in a way that will show how these two columns are similar. So I'll just take an arbitrary line that is parallel. Okay. Let's take an arbitrary line that is parallel. This is just arbitrary. Okay. Now you join this two. And this is a very important lemma actually in geometry. So, and you want to draw this line. So you want to show that this thing is equal to this thing. Yeah. So that pink line is passing through the concurrency point. And that red parallel line is anything. There is no ratio given. And it always ends up being the midpoint. Okay, so you don't have to do this now, but you can try this. And you can see how these two problems are actually the same problems. Later, you can try that. Maybe, yeah. You right. So, like, can you expand a little bit? Not, don't say the whole thing, but a little bit. Huh. Mm-hmm. Uh-huh. Yes. Mm. There is a area is equal. So you can try, but I don't know if that is the right, if that's a good way, but you can try. Yeah. There are many good ways. There are even some ways which you can do this in just one sentence. But just think, there are interesting ways. And you can understand that. Mm-hmm. 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 BDE and CD. Yeah. DEC, 1 second. So does everybody see this? Unab, do you see this? So because I think we had also discussed this once in your group, right? This DE is parallel to BC, so the areas of DEB and DEC are same. Okay, then. So then, yeah, what do we get after this? ABE. ABE and ACD. Ah, okay, that's good. Ah, okay, interesting. So area of ABE and ACD. That's an interesting perspective. Yeah, so you're just adding ADE to both the areas. Uh-huh. Okay. Hmm. Huh. Yes, it is. Okay, okay. I understand what you're doing. So you're kind of, as you said, you're replicating the proof of. Yeah, yeah, yeah. So along those arguments, it can be done. Right. But maybe, so that's a very special type of argument which you are giving, which is hard to come up with it if one doesn't know it from before. But still, I would want everybody to show that even if you don't follow this argument directly, try to do it in your own way. Show that BZ is equal to such. And what you're saying is obviously, and you can just apply Seba's theorem in this case actually directly and get the answer in one line. But okay, cool. So yeah, that's fine. Let's move to the next problem. Okay. So, so yeah, Unap, so this is not, today was not a class of your batch, but you can still do this class. I mean, you can do this class. There is no problem with that, provided because this mock test, but you have not written. So this is for the higher batch, but this turns out to be a simple geometry question. The next question is also geometry question. So maybe you can also follow that because we have done a bit of geometry with you. So yeah, so the next question, let's try. This is maybe a little more interesting. So this will be problem number 4. And so there is this triangle. So I put in 2 easy questions in geometry because usually geometry questions are not very difficult in your entrance exams. And I have not covered much geometry, so I just want that you can use this 15. And the next side is 15. And so then what is the question? M is a point such that the in circles of ABM and BCM are equal. So there is ABC. Okay. And M is a point on AC. Or some point here. Or maybe that is not good. Yeah, so I don't know. M is not the midpoint. Okay, just some point. So that the in circles. So just roughly drawing it. Okay. And ideally, I should have first drawn the in circles. And just checking the question again, they are of equal radius or in circles. Okay, find AM by CM. Okay. So maybe, so this is your gamma 1 and this is your gamma 2. Okay, so if gamma 1 equals gamma 2, which means yeah, radius is equal, find the ratio AM by CM. Okay, find AM by CM. Yeah, so anyone has done this? Let's see. Will they? So I don't know. I think they will, but you could tell the reason, or maybe not. Oh, okay, no, but in this case, the radius is equal. So you have to see what Chandan is saying here. So Chandan, are you using the fact that the radius are equal and that they meet at the same point? So, okay, so then try to say that more rigorously. I think it is correct. X, so what is X? Okay, so I just name it, then you say X, Y, Z, W. Mm-hmm. Huh. X and M. Okay. Mm-hmm. Mm-hmm. Okay, so I won't call it Y. Let's call it D. They are equal, yeah. Mm-hmm. Yes. Right. Yeah. So basically, you see the height YZ is equal to XW, right? So the height of both the things is the same, right? And so basically, it's just, you don't need so much argument here. You can just say it more elegantly. Maybe if you just draw this line, okay, this line is going to be parallel. Okay. Oh, no, 1 minute. Sorry, 1 second. No, 1 second. So what is going wrong? Okay, so maybe I will draw this. Getting a little confused. There is this and there is this. Yeah. So we are done, right? Because these two heights are going to be the same. Yeah. This heights. So this height is the same as this height. Is that right? Because the radius is same, right? And that height is the radius. So just say it once again. This, suppose this you call this T, then Tm is the radius of that of the gamma 2 circle. But if you call this some, I don't know. Yeah, so you see Tm is equal to Yz, right? Tm is the, oh no, because that is not, no, so it's not equal, sorry. Yes, no, yeah, that's not equal, sorry. Yes. Yeah, so okay, so I'm making some very silly mistakes, sorry. Yeah, so the Tm is, yes, yeah, right. The Tm is equal to mz, and say kite. But yeah, but they are not equal to the radius. So it's not a square. I'm sorry, it's obviously not a square. So we just have this. Okay, cool. Okay, so then how do we find AM? Sorry, DM and TM, yeah, but if they touch each other, but they don't touch each other, right? That is, yeah. Yeah, exactly. That is what we, but we don't have that. So then how do we do this? Is there a good way to do this problem? So by bashing, we can certainly do, because the in radius, which is equal, can be used to, relate the two triangles ABM, because I mean, you can relate the in radius with the triangle size of the triangle ABM, and similarly for this, there's this direct formula in terms of sides, and then you can equate them, and you can cancel things, and you can find AM by MCS, something like that. But can we do with maybe power of points or something like that? So let us think in that direction to find AM by MC. Even so, M is not the midpoint of WZ. Okay. So how do you use that? Yeah. So R1 equals to area would be a good thing, because area can tell us the ratio of AM and CM, so that may be not so bashy. And so this is S1, and similarly the R2 is and these are equal. So basically the del 1 by del 2, which is equal to AM by MC, is equal to S1 by S2. And then this is like C plus AM plus BM plus MC plus BM. So I don't know if this is useful. So we certainly know that this is true though. And so we can, so you guys know this, we can also subtract the ratios, right? Something like that. You can subtract the ratios and you can get that this is A plus BM. Yeah. So that's also called subtractor hendo, addendo, those kind of things. So you can use that. Equal ratios, you can say, I don't know if that is, maybe that's also called different books. But yeah, that name makes sense. But I will call it subtractor hendo. It's like there's addendo, right? Which you add the ratios. Anyway. Yeah, but this, so we don't know what BM is. Yeah, so certainly, so from here you can actually find BM. I mean, sense that BM can be found in terms of AM by MC, right? So you can use the Pythagoras theorem or Steward's formula, is that's what it's called. Yes, exactly, and that's what I'm saying. Yeah, so that's what I was going to say. So that will also be like a bash, but but yeah, Steward's formula is a pretty standard thing, or anyways. Yeah. Yeah, and also we are given the numbers, so you can just use that formula. But let's see if we can use something. Yeah, this BM is somehow a problem. Okay, but let's see. So call this X. Hmm. Yes, yes. Yeah, that can be done. Yeah, that I am fine with, that can be done, but we want to see if we can avoid that little bit. So this is a Z. So you see, I'm naming those pieces that you get, because I think with that we may be able to eliminate the BM. Let's see. So if this is W, it's W, then this has to be something else. U, and then this is V. So the BD is also V. So this we know, this is a very good substitution. Use this. Huh, that is true, because both are equal to BM. Uh-huh. Yeah, but the BM is not given. That is the problem. Yeah, that is the thing. So X plus, so we know, let's just write a little bit. X plus Y is 12. And V plus U is 13. And X plus Z plus W plus U is 12. But in this case, we are not able to use. Okay, no, wait. So. But we only have 4 equations. I think there is one thing that we can use. I think that is true. Is that the R1 plus R2? Is this true that R1 plus R2 will be equal to the in radius? No. Why? Okay. So I was just thinking that if you take any triangle and you draw any line and you take this in radius and this in radius, then do these two in radius add up to the in radius of the bigger triangle? That might just be true actually, but okay. Oh. Yeah, so we can maybe check it. Yeah, anyway, so let's not. So yeah, so maybe then we have to just do it in the bashy way, because I am not able to relate this. Look, but let's see. So if I draw this line, then uh-huh. Mm-hmm. Euler line of both these triangles. So they have two different Euler lines. So then coincident? No, how can they be coincident? They are different lines, right? What do you mean by coincident? I mean, no, they're not the same line, because they're in different triangles, right? Yeah. No, so the point is that we are not able to use the fact that R1 is equal to R2 geometrically. Yeah, so that's a bad thing. We are not able to do that. One second. So, my mind is not working. This is so. So if you okay, but I think we can say that if you that x, y, z, w is a rectangle, right? Yeah, that's what we should have said in the beginning. Yeah, x, y. I mean, I'm not saying that it's like they are cotangent, but x, y, z, w is a rectangle, that we can say. So I don't know if you can use that. Yes, because you can see, right? Because xw is equal to yz. Right. And so the situation is like this, right? You have XW. No, but you see, I mean, this is 90 degrees and 90 degrees. And if you're going to the same extent, then this has to be also 90, right? Like, what else can it be? I mean, so you have, I mean, this is just, yeah, I can think of it in many ways. I mean, heights are same. So XY is parallel to y WZ, you can say. Yeah. You can, yeah, so you can, yeah. Anyways, but that is fine. So that's a rectangle. So this is what I wanted to say in the beginning. I mean, so usually it's a trapezium, as you're saying. Yeah, usually it's a trapezium, but in this case, it's a rectangle. Can we use the fact that it is a rectangle? So we know that XY is equal to WZ. That's a, yeah, that is nice. Yeah. X and Y is 90. That is true, right? So why is that true? That's the correct thing. Okay. So let's assume this. This is true. Yeah, so that is 90. That is true. You can check that later. Yeah, I'm always thinking about the cotangent case. It is wrong. Uh-huh. Uh-huh. Yeah. And this is equal to this. Okay. So the situation is that. So this is the, so this yellow point, yeah, this yellow point is also the midpoint of XY. Yeah, note that. That way certainly, or I was also just seeing by similarity, XD is equal to YT, and you have similar triangles, right? XD and this yellow point, and YT and that yellow point. So they are similar, they're actually congruent triangles. So that way also, but that way of saying that's also obviously perfect. So this is the midpoint. M is not the midpoint. So it's a situation, I'm just drawing it separately so that I can, M is somewhere here. Yeah. MD equals XD. No. Okay, no. So D is not the circumcenter, right? The circumcenter, let's name this point. Let's call this O maybe. O. Yeah. So XO is equal to YO is equal to, right. So we have XO equals to YO equals to OM. That is interesting, but we're not getting anything, right? Yeah, इतने देर में this bashing is much faster, but this can we can learn some things from this kind of things which you can use in other places. Like you had done, so Adish had done some similar questions, so you are able to make so many observations. Okay, so just 2 more minutes. Let me think. Yeah, I don't know. Yeah, might be a connection, but anyways, yeah. So we observed these things, but I do not know how to use this. So anyways, the problem is done. I mean, the problem is done. For this actually does simplify the problem, right? Because this BM we can find in terms of the sides of the triangle and the ratio AM by MC. So if this ratio, you call this ratio lambda, then this will come in terms of lambda again. Just a quadratic, nothing more. Okay, Stewart's formula is straightforward. I can just use Pythagoras theorem also. So you assume AM by MC is lambda and you find BM in terms of that, sides are given. Maybe you have to do it like this. Yeah. I was thinking that if we this could throw some, because you see, PowerPoint doesn't seem to be useful because there are only tangents in the picture. There are no chords. So if there are chords and tangents mixed, then PowerPoint could give some new things. And also these are not cotangent. So how do I use any other things? Okay. Yeah. So if this 90-degree, if we try to use, then also it doesn't, yeah, seem to be useful. Okay, so then this is okay. We have done this problem and made these observations. Let us move forward quickly. So let's go to the next question. Now the next question will be non-elementary. So question number 5. Yeah, so question number 5 I'm not going to do because this question I have done in the class about linear functions, right? So yeah, so Adish and Chandan, so do you know how to do this now? Like the matrix view, you can try to use. Yeah, let's see. Yeah, let's just see this one. Yeah, so can you guys just see it, because that's a very straightforward thing. Because I mean, certainly if you're looking at functions from R3 to R, then obviously functions which kind of take an input x, y, z and multiply it with a matrix like this. These are your most obvious functions, right? Or you can just write it as ax plus by plus cz. These are your most obvious examples. And we had shown in the class that this is the only example. Okay, so any function which is linear as defined in the question can be written in terms of a matrix. Okay, so it can be determined in terms of 3 values. So let's just quickly see it. Okay, so the point is that let's say that you want to understand the function at a certain vector, because the input is a vector, right? The input is a tuple. If you want, I can write in both the languages. So I can write it as x, y, z also. Okay. Now the point is, let's just use this language only. You can break this up using what we are given. Let's write it directly as the input on this 1, 0, this is unit vector, and the input on, yeah, so you can see that this can be done. and then we have Z, and then again you can see that this can, and then that's your matrix, right? So you know what your matrix is. I mean, these three are the, I mean, basically you have found all functions. You will say that these, I need to decide these three values. And so this, it will be your A, this will be your B, this will be your C, and this, everything else is determined. So it will be of this form. And now whether you want to write it as a matrix or not, that's up to you. You don't have to, but this tells you all. It's a very short thing. Okay, it's nothing non-trivial, but yeah, you have to be able to use linearity. Okay, linearity basically tells you that you need to know the function on only three values. Okay, and that's it. Three values if you know. In fact, if you know this function on any three values which are suitable, they're general, any three values will tell you the entire function at every other value. Okay, you can think about this. So maybe I can write it as a question. Okay, if f v1, f v2, f v3, so these three are the some three vectors are given some numbers, you know, some numbers, three numbers are given to this. Okay, then fv can be found for any v. Okay, so v1, v2, and v3 are these three vectors are in general position. Yeah, you can interpret what that means. So they don't form a plane. Okay, like you have three vectors and they don't, their endpoints. No, not their endpoints. Yeah, when you have three vectors, like two of them form a plane, right? The third one should not be in that plane passing through the origin. Okay, so yeah, two vectors, they form a plane, they form this plane. The third vector has to be somewhere in a different plane. That's what it means to be in general position. If this is in general position, then given any three vectors, values at any three vectors, the whole function can be found. Okay, so this is a simple question. So just see if you have any questions with this, you can ask. And you see that this view is very important, like so many matrix problems and so on. If you see a matrix multiplication as this, then it can, you know, you can say a lot of things about injective implies surjective or whether injective is possible and so on. You can say, because this function view is good rather than just an array view, which is useful, but yeah. Okay. Problem 6 we discussed. Let's discuss problem 7. Okay, so problem 7 is a good one, I think. So this is about discontinuous points of a monotonic function. Discontinuous points of a monotonic function. This problem is intentionally a little vague. I want to see what you guys interpret. I'll just write it here. Okay, so pick a point at random. So let me just write it. So you guys frame the argument. I want to listen. Because you have written it's good, but when you try to say it, you can I can say more. So R to R and pick a point at random. Okay. This F is monotonous. F is almost surely continuous at F. Okay. So I want to hear what you guys, it's not continuous. The function is not continuous, okay? Obviously, otherwise. So what do you make of this question and what do you try? Yes, yes. Mm-hmm. That's mm-hmm. No use in what way? No, but see, if you have a function from n to n, then it has to be continuous, right? So that's the thing. Any function, well, it depends on what. But if you think about it in the usual sense, then and this is a good one, good conceptual thing to have in mind. Any function f from n to n is continuous. Any function. If you disagree, so if you guys disagree, then tell me. Otherwise, try to prove it. That's why we never study continuous function. Yes, like this. Yeah. Oh, well, that's different. Yeah. Yeah, that's true. That's true. Yes. Sorry. But they're not onto, right? They are not also almost onto. You can think, you can construct many functions like this. You can take it to whole. You can skip as many intervals you want, right? And it is monotonic, but certainly not. You can not onto. Yes, that's true. Yeah. But what about this point that any function from n to n is continuous? And that's good to understand. It's simple. It's a silly thing, but we should understand it. Uh-huh. Mm-hmm. Mm-hmm. Yeah, you can take limit of sequence, or you can just take the epsilon data definition, right? So basically, you have to form a small enough epsilon for every epsilon. Yeah, you take this epsilon, and then you get a delta. What should that delta be? Then you just take a delta of length less than 1. It will not touch any other point in the domain. So, huh? Yeah, you get very large margin to do. So for any epsilon, you just take delta small enough, and then there is nothing to do, right? Okay. So that's the thing. Now you guys can think about this n to r. Okay. This, and also I think this is not very interesting. What is more interesting is this, or just z. That doesn't matter, but let's put it z for safety. Continuity. These two are very interesting questions. Continuity of. At least the second one is interesting. Mm-hmm. 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 Yeah. No, no, it is not monotonic. This is not, these functions are not monotonic. This is an arbitrary question. Yeah. And yeah, maybe that's all I should say. There is more thing, but this is, yeah. Okay. The first question is not interesting, but the second question is, I think, fairly interesting. So think about it later. Huh? What is discontinuous? So not every function is continuous, it's true. Okay. But yeah, that I can understand what you're saying. Yeah, certainly. It's easy to make examples, but can you describe what kind of functions are continuous? What kind of functions from R to Z? This is a very good variation, because usually we study continuity from R to R and everybody is pakka with all the tricks. But this is a, okay. So what kind of functions are continuous from R to Z? Can you describe them? Okay. Um, yeah. Like if you take a constant function, then that is certainly continuous, right? Any constant function from R to Z is continuous. But okay. But let's say that if there are two, I don't want to say anything more. Okay, just think. Then it gives the answer. Uh-huh. It should be increasing, but its answer is more specific than that. Much more specific than that. Okay. Think. It's a really cool answer to this question. But let's come to our questions. Okay, so what I mean by this question, yes, yes. Mm-hmm. Mm-hmm. I don't agree. Or do I agree? No, I don't agree. That's not true. So if you're saying that if it is discontinuous at C, then it is not covering C, but that is not true. You can just take some, yeah, anything. You see, this is again, yeah, it is discontinuous at A, but it is covering A. Mm-hmm. Right. So basically, you want to say that if it is discontinuous at some point, then that point is very special. The points where it is discontinuous are not too big or something like that. Yeah, so so that's the thing. Try to consider an arbitrary point at which it is discontinuous and try to see what you can say. So if, okay, so just think, I also have to think. So rather than making the question concrete, let us just take a point where it is discontinuous and see what we can say. Right? Otherwise, trying to make the question concrete from beginning will make it just more theoretical and not very I mean, it's good, but if let's say that f is discontinuous at x naught, discontinuous at x naught, then what can the situation be around x naught using monotonicity? So let's say it's x naught. This is f of x naught. So f of x naught is obviously in the range. Monotonic. So what kind of discontinuity can it be? What's the first guess? And try to prove that then. Okay. Yeah. Okay. Okay. Mhm. But I don't understand. No, so all the points need not be covered. So A is in, so you're saying A is in the range and B is in, okay. So let us then not write it as A and B, just to be, let's write it as, let's say f of x1 and f of x naught. But so then you're saying are all the values in between attained? That is certainly not true. In between, no, that is not true. You can skip most of the value. You can skip a lot of value. So you can take something like this, right? And then you can take something like this, and you can skip one. But yeah, so many things in between are skipped. Yes. So yeah. So what I mean by this almost surely is that the probability that the point is continuous is, or rather, let's say the probability that the point is discontinuous is 0. So probability that x is f is discontinuous. I'll define what probability means in this case, and it is not very far-fetched. I will show f is discontinuous at x. This probability I want to show is 0. Okay. What do I mean? I mean, this is over an infinite set. So what do I mean? So I mean that basically what I mean by this probability is that area, okay, area of the of the points of discontinuity, yeah, area of discontinuous points. I want to basically show that this area is 0. Yeah, and we have defined what area of sets means. Yeah, and I want to show that the area of this set is 0. Okay. Now, in an exam situation, what could happen is they can first describe the area of sets, or they can simplify the question in some other way. But you have done this in many ways, geometric probability problems, right? Where you will be this, and then there'll be a circle or some other shape, and a pin is dropped at random. What's the probability ends up in the circle? So that's the area of the circle divided by the area of the figure, if you take that as unit or whatever, right? So that's the thing. The similar thing I'm trying to say here. So I'm trying to basically say that the points where the function is discontinuous, their areas is that area is 0. Okay, but how would you show that area of something is 0? What all do we know? It cannot be a very difficult question. So what we just want to show is that this set of points where f is discontinuous is countable. I mean, that is the most natural way in which area can be 0. That's maybe the only thing we know. Well, there are other examples we did, but it's the most natural thing. If you can show that the set of points where f is discontinuous is countable, you can list them, then you can certainly show the area as 0. You can show the area smaller than anything, right? We had done like the natural numbers have 0 area, rational numbers have 0 area, same reasoning, any countable set has 0 area. So if you want to show that the set of points where f is discontinuous is countable. Okay, that is the thing. So you can note, this is the thing what you have to show. The set of points where f is discontinuous is countable. Okay. And now that you can try to do, because see, every discontinuity point is in fact a jump discontinuity, because left limit will exist and right hand limit exists. So now you can think on this. Yeah, see, every time you're having a discontinuity point, you're kind of having a neighborhood, which is, yeah, you can think. So you're kind of getting a empty place and so on. So yeah, so you have to think. Yeah, so you have to think using this. Basically, you have to try to show that it's a countable set. So this you can try on your own, and then we can discuss this next time. Yeah. So now you see we are remaining with 1 or 2 more questions, 2 more questions. So I will not do this today. Like already we are way out of time. So maybe we can. So next time we will not begin with this. We can do with the integration problems that I had in mind, and then that time we can chip in those 2 problems also. But first we'll begin with that. Okay. So I think then I'll stop today. Okay. So I've given you the hints. Okay, it's about this, at any point of discontinuity you have, then in a neighborhood you kind of get an empty thing. And so now you can think. Uh-huh.